Hello everyone, this is Anupam Nayak. Today I'll be talking about coding computing techniques for Straggler mitigation, security and privacy along with my teammate Param Rathod. So this is an overview of whatever we'll be covering. The first part includes Straggler mitigation in distributed matrix computations. The second part includes Lagrange coding computing and basically going beyond matrix algebra and some applications. So the basic problem setup I'll be describing now. So we have a matrix A. We have two matrices A and B with entries from a finite field of size Q, and the dimension being S cross R and S cross T. And we intend to compute this product A transpose B, and it is implicitly assumed that one of these matrices is tall. So we basically have n workers or n servers on which we can perform computation. So our objective is to distribute the task among these n workers so that in such a way that if there are stragglers in those n workers and just k of them give us the output, we are still able to recover the product correctly. So we assume that each of the n workers stores 1 by m fraction of A and 1 by n fraction of B. So this will be effectively the dimensions of AI and BI. So the idea here is to somehow use MDS encoding such that if we generate only k out of this n workers, so the ones which generate the output the quickest, and we'll be able to use just those outputs to successfully recover the product C equal to A transpose B. This is just a visual diagram of what we are trying to do here. So yeah, computation strategy. So computation strategy is basically a set of 2n functions, f0 to fn minus 1, g0 to gn minus 1, that are used in our encoding. So AI and BI are defined like this: fi of A and gi of B. And for any integer k, we call this set of functions as k recoverable if just k out of the n workers ka output can help us recover the product correctly. So we define k of f comma g as the least integer k for which a system for a fixed f and g is the k recoverable. So it's the least integer for which we can recover the product correctly. So we similarly define something called as optimum threshold. So that is the lowest of the recovery threshold across the set of all computation strategies, as in if f comma g are it's the minimum of this recovery thresholds among the set of all functions, possible functions for this f and g. So the current schemes which are generally in use are 1D MDS scheme. So here you could see that the optimum recovery threshold is this expression, and we could see that it is of the order n. And similarly, in the same paper, it's given in the references, another scheme is described called as product code, which is for the special case of m being equal to n. And there we'll have the optimum threshold as in the minimum workers from which we would require the output, growing as square root of n, so it's order root n. So these are okay. So this the main result of the paper I have surveyed is that the optimum threshold for matrix multiplication is m cross n, m into n. So this is not the capital N, this is the n as in the fraction of B that is available to each worker. So, and further we say that there is a computation strategy referred to as polynomial code, which achieves this threshold. And we also show that there is an efficient decoding algorithm that can help us find this using polynomial interpolation, basically. Using just m points. Decoding polynomial codes, yeah, so this was basically covered in the class even the Reed-Solomon decoding algorithm could be used for this purpose for the last step. So this is related exactly what was taught in the class. So I'll just be covering the main proof of the theorem. Before that, I would like to show a graph. So these are the common techniques used. So you could see that this is, as we described, the optimal polynomial code. With increasing the number of workers, it's the recovery threshold stays the same, m dot n, for the fraction being stored being the same. But for our MDS code, MDS scheme, 1D MDS scheme, this increases with the order n. So this is essentially, it will be one of like uncoded repetition or short MDS. The number of workers from which we would require the output, we would like it to increase with n. And bilinear complex also has a constant threshold, but it's higher than whatever we have for the polynomial code. And this special scheme for m equals to n would increase as square root of n in this graph if it was plotted. So it will be under these two eventually, but yeah, it will still be an increasing function with n. So yeah, so I'll just briefly sketch out the proofs of proof of this theorem. So there are many results in the paper. One of the most important ones I felt was this. So I'll just briefly sketch the proof for you. So we are given parameters alpha and beta in n. Not given, actually, we have to choose them. So yeah, so we just define AI as our polynomial code, AI as this thing, polynomial encoding. So this is basically your 2n functions. So this is your computation strategy. And similarly, we define beta as bi as sigma bj into xi j beta and summation from j0 to n minus 1. So simple algebra will tell you that the ith ci will be this thing. The product of A transpose B will be given by this expression. So now we see that these xi's anyhow we'll be using some distinct xi's for our evaluation. So we have to be worried about this power here. So we have to see that no j alpha plus k beta has an overlap. So no for no two values of j comma k, the exponent here should have the same value. So one such choice would be to use alpha equal to 1 and beta equal to m. If that happens, then we'll have our hx defined as for some xi. I fixed it as x here. Hx will just become this. Your alpha is 1 and beta is m. So yeah, so this beta should be m here. And this so this is a polynomial of degree mn minus 1. So beta is equal to m. So the polynomial will, the max exponent will be mn minus 1. You could check it. And since xi's are chosen to be different, so we essentially, in order to get back our ci, we just need output from mn workers. So basically, we want to show that we want to perform polynomial. We would like to perform polynomial interpretation, interpolation, and find out this, recover this product ci. Or otherwise, we could also use the any Reed-Solomon decoding algorithm, and that naturally happens to be the faster way to do it. So yeah, so far we have shown that there exists a scheme which attains this mn threshold. Now we want to show that this is the best you could do. So you cannot have a optimum recovery threshold less than mn. That's what we would like to show. So without loss of, so I'll just briefly sketch the proof here, the main steps. So without loss of generality, we'll assume that A is an arbitrary fixed tall matrix. So one of the two has to be tall. So we assume that A is tall with S greater than or equal to R, and B is sampled from a uniform distribution over FQ S cross T. So one can check that this distribution, So one can check that the distribution of product A transpose V will be uniform over this thing, over this space. This means we need to recover the random variable whose entropy is RT log Q. So we have RT entries in this matrix and each has an entropy of this much. So we need to effectively recover a random variable whose entropy is RT log Q. Since each worker outputs RT by mn elements of FQ, we would at most require, it will at most provide us with RT by mn log Q bits of information. So total information in the random variable is this much, and a simple division would tell you that k has to be greater than mn, because this is the max a single worker can provide. So we'll have k greater than mn. So I'll have to say the performance of polynomial codes over some other evaluation metrics commonly used. So the proofs of those have been discussed in the paper. I'll just be highlighting the results here. So the computational latency is defined as the amount of time required for the master or the main centralized server to collect enough information or enough bits, as in get output from enough number of workers. So in order to decode C. So for any other computation strategy, we'll have the computation latency time will be greater than whatever we have the computation latency for polynomial code. And so there is another metric which is known as probability of failure given a deadline. So we have an arbitrary deadline, and the proof for this very much follows as a corollary for the proof of the computational latency being optimal. So probability of failure given a deadline is defined as the probability that master does not receive enough information or less than the optimal threshold number of workers produce output at any given time t, which is predefined. So the result here says that the probability of failure given a deadline is higher for any other computation strategy when compared to probability of failure for our polynomial code. Similarly, another metric is called communication load, which is defined as the minimum number of bits needed to be extracted in order to complete the computation of or the successful recovery of our matrix C, of the product matrix C. So which is upper bounded by this thing. And this is achieved by the polynomial code. The proof of it follows very much like this, with a minor tweaks here and there. And yeah, so next part will be discussed by my teammate Param Rathod. Param, over to you.
So till now we have seen the problem of matrix multiplication. Now we will go beyond that matrix algebra and we will see the problem of polynomial evaluation. So we have a distributed computing environment with a master and n workers. We have a data set which is x1 to xk, where every element is an element of some vector space over some field. And we have a multivariate polynomial f with vector coefficients and degree denoted by degree f. And what our goal is to compute this y1 to yk, which is f of x1 to xk. So we want to somehow distribute this x1 and xk into n workers and get the output. And the thing is, so what is happen, the ith worker, it will not store the x1 to xk, because we also want to do the Straggler mitigation and other things that I will discuss later. So ith worker will store some of gi of x1 to xk, which can be even random, or so all these technicalities we will discuss later. And we have a notation where I belongs to bracket of n. So bracket of n is just 1 to n. And each worker will compute then this y tilde of I, which is the function when it is applied to x tilde of I, and return the result to the master. Then this master will wait for some fastest workers, and so what is the amount of workers that it has to wait and everything, that will depend and on the algorithm. and then the master can decode and get the output. So we will consider linear encoding strategy, where means the GIs and all are linear combinations, so there is not much calculation to be done at each worker. So some examples before we proceed. So to see the application of polynomial evaluation. So suppose we want to consider A cross A sorry A B bar for some data set A is equal to AI. So this is a vector B. So this is a column. We have k columns and it is a matrix. So we can see the suitable V as vector spaces and U as, and then we can define a function which is xi dot b bar, and using this the where xi is AI, and using this we can get the outputs y1 to yk. And say we have a bilinear computation where we are doing an element wise product of two matrices. So here we can have V as the space of pairs of two matrices and U as space of a matrices, and Xi is tuple AI cross B, AI comma Bi, and then f of Xi is AI dot Bi for all I belongs to K. So obviously the dimensions have to be assigned suitably to this field to these vector spaces. So now we will see the result, that is the minimum possible workers required if some workers are failing, or or even if they are not, or if they are delaying. So what is the minimum possible workers with which we can get the computation back? So if we have this function f, then the minimum possible workers is denoted by k star. So at least this many number workers will be needed by any algorithm, and which is equal to k minus 1 degree f plus 1 if n is greater than equal to k degree f minus 1, and if suppose n is smaller than this, then it is this condition. So now here's the crux of our approach, the approach that is discussed in paper, that is the Lagrange coded computing. So the framework is such that it achieves this optimal k star. And so how do we prove this? So that will come up later. Before proving that, let me tell you that this proof is a bit involved of how this minimum, what is the minimum recovery threshold for any arbitrary polynomial function, multivariate polynomial f, and so we will not include that. Instead I will prove this that the Lagrange coded computing is optimal given that this is the k star that we can get. So first we will brush up our 605. We have studied polynomial interpolation in the Reed-Solomon decoding. So it is just when we are given n plus 1 data points, we need to calculate a polynomial that passes through all these data points, and so the degree of polynomial will be n, and then that polynomial can be given as p of x is equal to this a n x1 plus so on. We can just take the coefficients as some variables, and then we can construct the polynomial using this system of linear equations. So each equation here is just a evaluation p of xj equal to y of j. Okay, so now what we will do is, so the Lagrange coded computing does similar thing, but it's Lagrange interpolation. So in Lagrange interpolation, we have p of x is equal to this term here, summation of summation of some products. So what it does is that suppose we have, so first we will just consider at the point x0. So what it does, this is the function, this is the sum for x0, and here you can see that if the point is x0, this fraction will be 1, and if suppose it is anything other than x0, say x1 x2 xn, the other points that we are evaluating, then this will be 0 because of these terms. And similarly for the others, so in intuitive way I can say that one thing will be a non-negative and others will be 0, or even this can be negative, this can be, sorry, one thing will be non-zero, and all the others will be 0. So if the polynomial is actually evaluated to 0, then everything will be 0. So suppose this is the first point x0, this is x1, this is x2, and this is x3. So we can see that uh, that all the others are 0 here, and only this is uh, something different. So this is different because we are scaling it by whatever is the polynomial's evaluation, and then what we are doing, we are just adding it, and as others are 0, this addition will work perfectly fine, and we will get this black polynomial which passes through all the points. Okay, so the Lagrange coded computing, the key idea here is to use this interpolation polynomial to somehow create this computational redundancy across workers, and then each worker can do some computation where they will evaluate this polynomial. Remember that the worker also has gi, so it's not just xi that the worker has x tilde I. So this will mean some composition of a polynomial gi and f, that we can say as hi, and then the master will decode this using only k star of hi. So this, why only k star, this is because of Lagrange coded computing. Okay, so how is the encoding done? So first of all, we can select any k distinct elements, beta 1 to beta k, from the field, and we just find the polynomial which passes through all these elements, such that we say beta I is u of beta I is equal to xi. So this can be just accomplished by Lagrange interpolation polynomial, as we have seen before. And now what we do, we select n distinct elements alpha 1 to alpha n, and encode the input variables as u of alpha I. So this x tilde is u of alpha I. So what happens in this phase, that x tilde can be written as some linear combination of this kind of, where there is every vector, every this xi data set part, and we have this product term. And now so that's how encoding takes place, and then the workers compute it using this y tilde is equal to f of x tilde, which is equal to f of u of alpha I, and send this y tilde to master. Now suppose we have this composition, so it will be also a polynomial which will be f of u of z, and the degree of it will be at most k minus 1, which is the degree of this uz, and degree of f, so it will be multiplication of them. Okay, so now if we have any k minus 1 degree f plus 1 workers return the evaluation, then we can again construct this polynomial back. So we don't know this before, the master doesn't know this, but after getting this k minus 1 degree f plus 1 workers result, it can construct this back, and then we can just evaluate it back again at beta i's to obtain f of x i's, and in this way we can get the y1 to yk that we are having. So one thing that is missing is that their number of workers, the second case here, this one, when the number of workers were less, this case. So what happens in second case is, so the way to prove this is, if suppose it is very small, then Lagrange, instead of using Lagrange coded computing, we can just replicate every xi by n minus k times, and then every set of n by n minus k plus 1 computation will contain at least one copy of f of xi for every I. So that's the one way. Okay, so now we move to secure and private multi-party computing. So we have this data set. Now here is the thing, because it's multi-party, it need not be so we cannot trust every worker or uh, that is happening here. Some may try to give malicious information, wrong information about the answers. Some may try to get what is our data set back. So if you want to make a data set private, then this is a bad thing. And we also just have some stragglers which are giving it delay, and some normal fast workers depending on the function we are computing. So first thing we will see is the systems. So in a S resilient system, the master must be able to obtain the correct values of all these y1 to yk, even if s workers fail. So that then it's a S resilient system. Similarly, in security, if suppose there are A workers returning arbitrary erroneous results, something, or they are trying to give us bad results. So then, even then, we should be able to retrieve the correct answers. And privacy means there are T workers who are colluding and trying to get the information about the content of dataset. Even then, they should not be able to get the information. So this is the mutual information between X and the subset, such that any subset which will, so that mutual information should be equal to 0. Okay, and this tuple SAT, these are also called parameters for resiliency, security, privacy, and is achievable if there exists some encoding decoding scheme that can complete this computation in the presence of these many number of different stragglers, adversary workers, colluding workers. The adversary workers are also called Byzantine workers. So the generalized result of linear Lagrange coded computing is this. Now notice that this here, what it says is that we have S, we have A, we have T as here, and this in a way this is very similar to what we have studied before. If you remember, so I will just give a hint here. Let's suppose we add one additional worker, that it can increase the resiliency of the stragglers by 1, robustness to adversaries by half, while maintaining the privacy constraints. So, so this is similar in a way that suppose we added a Hamming distance of 1, then we get one erasure more or half error correction more. So it's not just a coincidence. The proof of this really proof of the optimality will of this, that this is the minimum, will include, will have some similarities to that. So you can think about it. And here the encoding and decoding part is very similar. So the only thing is that now we are adding an element of randomness. So because the worker should not be able to get the information by colluding, randomness is necessary, and that's why when I told it before that GI should be random, can be random, that will help here. So it's the same thing, this one, but now we are adding T more workers, so T more distinct elements which will be distinct from all these, and those elements we can then have some random. This is also ZI also randomly generated, and we can make this polynomial now instead. So what this will do is that now if we select any n elements, the xi will be given by this kind of this tuple multiplied by this ui. So where u is a 2D matrix of infinite field fq, and its element are also again this Lagrange this multiplication without the scaling. Okay, so the decoding is done similarly. The only difference in the decoding is that now the master has to obtain more evaluations because there are some of incorrect, and we can again apply the Reed-Solomon decoding and other algorithms if the degree is greater than this, and then master can evaluate and get the answer. So this is hence in this way we can see that the above scheme is S resilient, A secure, and also T private. So the T private proof is a bit more complicated, and hence I have not shown it here. Okay, so that's it. Now here we can discuss some open problems. For example, if we want to not have a master, so what happens then? And suppose we want to do even more than polynomial computations. So this is very important in machine learning. And suppose and in blockchain. So in blockchain systems, we have this dilemma of decentralization, security, and performance scalability. So that also can be done using this coded computing research. Okay, so that's all from my side. Thank you. These are our references.
Thank you.